Hi, I'm Dr. Jim Overholt, Senior Scientist for Autonomous Systems at the Air Force Research Laboratory, and today I'm joined by Ms. Chris Kearns, who's a Portfolio Manager for Autonomous Systems across AFRL, and together we're going to talk to you about the Air Force Research Laboratory's Autonomy Science and Technology Strategy.
This is our final goal that we're going to talk about. What we've done so far, I think, is we laid out the overall vision and strategy of what we're talking about and how we break those down into goals. Today we're going to dig down deep into our fourth and final goal that is very important. But before we do that, let's give you an introduction and make sure that we're all on the same page as far as what is our vision and what are the goals that we've talked about so far. So our vision is really about intelligent machines seamlessly integrated with people. And then we like to say there are a couple of things that are important in that. It's the intelligent machine, so we are talking about machines that have the capability to understand their environment and make decisions about that and what should they do, but they are seamlessly integrated with people. So we're not talking about taking people out of the mission, but how do we put machines that are intelligent together with people so that we can maximize the performance of the mission in complex contested environments that we, the military, have to operate in.
Absolutely.
So when we came up with our vision, then we said, so what are the major goals? What are the challenges that we're going to have to address in order to achieve that kind of a vision? And we broke that into 4 goals. Like I said, we've talked about the previous 3 in previous recordings, but just briefly, they are how are we going to demonstrate these highly effective human-machine teams? How are we going to have people and machines work together? The second goal was about how we're going to have coordinated teams and machines. So just like we have people and machines working together, we want machines and machines to be able to work together, coordinate and do work. How do we make sure that they can operate in the complex contested environments that we, the military in particular, will have to operate in, which doesn't preclude non-military environments, but it's a lot of focused on our military environments. And then finally, the one we're going to talk about today is how do we ensure safe and effective operations? In other words, how are we going to test and evaluate, verify and validate systems that make decisions and can have the capability to make decisions in environments where they're unanticipated and they're dynamic, so that we don't really know what exactly the environment is going to be, and it's going to be changing when we get there.
And these are systems that are heavily or intensive software involved with them. So yeah, this area is something that's really critical for us to be able to roll these systems out.
So just like our other 4 goals, what we did is we took this one and said, so there are some long-term enduring problems. There's some research challenges that we're going to have to take on. They're not quick fixes and they're not things that we can just resolve and move on. So what are the enduring problems that we're going to have to investigate and work towards in this test and evaluation, verification and validation? So we break those into, actually on this one, it's 4 areas. The first area is about making sure that we have the assurance technology so that we can assure that the machine intelligence and the decision making is correct.
Okay.
So it's about making sure that that system is making the right decision.
That's important.
There's a component then of how do we make sure that the architectures are easily verified and validated so that we can not spend decades making sure that these things are making the right decisions.
Absolutely.
So underlying in that is that whole how do we make sure we have rigorous and verifiable architecture systems. Tied into that, though, is also we want to make sure that our systems are making decisions on the right data.
Yes.
So there are people out in the world who would want to scramble the ones and zeros of data that a platform is pulling in and making decisions on. We want to make sure that when that system takes in that sensor data, that it can verify that this is valid data. Someone isn't sending me a different command that isn't what I'm supposed to be doing. And so we want to make sure that they have that underlying security in that framework to make sure that it is making decisions on solid data. Previously, we've talked about we want a single intelligent machine, but we also want to incorporate machines together and teams of machines to do things. Once we do that, then we're also going to have verification and validation strategies on how do we make sure that as teams and machines work together, both as teams, fractionate and then recompose to do things, that they're not displaying any emergent behavior that we wouldn't want them to have.
Right.
And so that's another one of our enduring problem areas. And finally, because we talk about how do we seamlessly integrate machines and people, we have to be able to test, we have to be able to verify and validate that when we bring people and machines together, that the communication and the interaction is exactly how is optimized.
Okay.
In other words, if we're going to put a person and a machine together, well, ideally we would like to see is 1 + 1 is greater than 2. Yeah. How are we going to test and verify that actually 1 + 1 is greater than 2? And so these are all the long-term challenges under testing and verifying, testing and evaluating, verifying, and validating that these systems.
And those are significant challenges,
right.
Every single one of them.
Right. So then we take each one of these and we talk about what are the key challenges? What is the key challenge? We haven't really said that testing and why is this a hard problem?
Yeah, and you know, when you look at that, so again, we're talking about these extremely highly complex, software-intensive problems. So you cannot wait until the very last rollout of the software to do the kind of testing that we need to do. So the fact is that we are taking a multiple number of systems, all with their own capabilities. Some we call them modules if you want to, or call them subsystems. There's software associated with that. And as we start adding these systems and they start having more and more effect on each other, you can imagine the testing and evaluation could get really complex. And we can't possibly test for all conditions that these systems are going to have. So you have to come up with some kind of methodology that allows you to test for the, if you want to say, like the design of experiments, these kind of things. So, I mean, these are one of the really important features, is the fact that you can't test for everything. And you touched on a real important part, too, which really is a fear, is something that the community is worried about, this notion of emergent behavior. As these systems get so complex, and mostly from a mathematics standpoint, what we would call they're nonlinear. They don't have real nice smooth behavior that we can predict necessarily. And people are worried about this notion of emergent behavior. Will something come out of the system that's unanticipated and will perform in such a way that it does harm, or it significantly degrades the performance of the autonomous system? So these are some of the kind of things. So the cost and the test and the cost of software, looking at the fact that we can't possibly expose our systems to every possible state or situation it's going to see, and this worry and this concern that unanticipated, undesirable emergent behavior is going to occur. So these are big challenges, so to speak, or issues right now with highly complex autonomous systems that we need to solve in order to roll this technology out to the warfighter, to the airman.
And when we say complex systems, what we are really, I think, talking about are these are all software systems.
They're mostly software with mechanical, obviously, right, electromechanical systems.
And there are, I think you were telling me, you know, there are systems already out there that have hundreds of thousands of lines of code already.
Millions in many cases,
so making
certainly.
Sure that that code all got put together, and as it was developed in pieces, how do you make sure when the pieces come together that they're communicating and they're sharing data and everything is fluid and not creating any disturbances in the behavior of the system.
And certainly it's not necessarily our background, but there are people obviously involved with the notions of formal software and being able to roll out this kind of software. So certainly we're going to look to that community in order to help us solve these kind of problems, especially when you have a system potentially making the decision on its own.
And what we know is in today's environment, the way that we, the Air Force, test our systems is essentially what we do is we set, here's the performance envelope, and we test right up to that performance envelope to make sure that the systems are going to perform the way they're supposed to. When we start talking about dynamic, unanticipated environments, first of all, I can't set that performance envelope.
You can't, that's exactly, that's an infinite state.
It's unanticipated, right? And if it, even if I could, now it's also changing. So how do we test using the current regulations that we have in the Air Force? I think we've kind of come to the conclusion we can't. We're going to have to figure out other ways to be able to provide the evidence, to provide the confidence, and to instill the right level of trust that these systems are going to behave, they're going to perform the way they're supposed to, and probably most importantly, they're not going to perform the way we don't want them to.
Absolutely.
And so I think, you know, knowing that, we've started to dig into this problem, and we've dug into and starting to identify. I think we have 5 areas that we kind of say these are technology development areas that we think we're going to have to invest in to be able to eventually be able to field systems that make decisions.
And Chris, let me just, before you go into, you know, talking about those areas, it's really clear within the DoD right now that this is an important feature, but we're not necessarily putting the resources in order to tackle this problem. You know, compared to the other things we talked about, whether it be the human-machine teaming or the machine-machine teaming, certainly we're putting the resources. Here at AFRL within the Air Force, we realize how important the problem is to this. So a formal activity in really getting down into the science and technology, which is very unusual for looking at things like you said, a testing and evaluation, validation, verification of these highly complex electromechanical software systems that make decisions on their own.
So I think what we're exploring is like I said, if you look at the way we do things today, we test it.
Yep.
Are there other things that we possibly could do, in addition to testing it, to be able to provide the data, the confidence, all the evidence that would be needed to
simulations,
say
exactly.
this system is going to behave. And so one of the first things that I think we would identify is we would say, what we really would like to do is do a better job of accumulating the evidence from the development all the way through what we call developmental tests through the operational tests that we do before we certify a platform to go.
Great idea.
So why not find ways, especially when we're talking software and we're talking code development, is there a way to cumulatively create the evidence that is required to show that this system is going to behave, it's going to do the things we want it, or more, like I say, most importantly, it's not going to do the things we don't want it to do.
Right, I agree.
Yeah. And so part of that starts with, can we also then create the evidence during design?
Oh, yes.
That says, we have designed this system and we have put in the tenets and the hooks to be able to ensure that it's going to behave.
So
that we make it testable as we design it so that you can start exploring that operational space
so kind of
early.
like a test often, right? As you're designing, why not test as you're designing?
Right.
Okay.
And put the hooks in there to make it be able to, you know, in the code that you can just immediately kind of run a test quick and be able to do things like, for instance, something as simple as if it's a flying platform, if the platform is going to go this way, put a shadow ahead. So that you can see what decisions it's getting ready to make, and you can validate in real time that it is going to make the decisions you want, which kind of leads us to one of our areas, which is how do you do runtime monitoring?
Oh, yes.
Can you, in real time, as the system is performing and doing its thing, can you monitor what's going on, what decisions it's made, what evidence, what sensor data it's taken in that led it to those decisions, and in real time monitor its decisions, so that if it's going to do something you don't want it to, you have the opportunity to interfere, redirect it.
And that's an important feature. So in some ways you can think about it, is it like an outer critic or an outer loop in a way that looks at the decisions being made and tries to, if you want to call it, rein in or correct for things that maybe start going out of bounds of the kind of things that we wanted it to do.
And in my simple mind, it's not like being a parent, right? When you have a little child, you're pretty much directing them and guiding them along the way. As they grow up, you give them a little more leeway, but you're still monitoring. Eventually, they need to be able to work on their own, but there is a time during their development that you're kind of, if they're heading off in the wrong direction, you have the ability to re-steer them and say, no, let's talk about that decision.
Not my kids. Yeah.
And why did you make that decision? And maybe we can help you readjust your thinking process so that now you can make a decision that maybe we think is a little more appropriate in that situation.
Yeah, excellent. That's an excellent description.
Yeah. One of the other areas that we've identified that we talk about is we need to do better about creating the standards up front, so that allow us to do the test and allow us to do all the traceability that we've talked about.
That's a great point. I mean, standards sometimes and requirements for these things, they get so complex, and being able to check that the requirements themselves are not conflicting. So, you know, work a design where you'd have two different requirements that have come together that are actually asking the system to do two separate things at one time. That's a critical area, and surprisingly, not necessarily a lot of work in that area.
Yeah, yeah. And then finally, one of the things that we need to get better at least from a DoD perspective, is be able to reuse the evidence.
Oh, yes.
So if I have created an algorithm and I have created a certified platform, and now I want to add in something new, do I really need to go back and recertify the whole thing? Or is there a way that I can certify the component, do a quicker recertification of the pieces and parts, and be able to get to reuse the evidence that I previously have had?
The previous evidence,
so,
right.
Yeah, yeah.
It almost sounds like you're making a case in a court of law. You
Exactly,
know what I mean?
right.
Okay,
So
okay.
if we can start thinking about our V&V process, our verification and validation process for these things, similar to I'm a lawyer, and I'm trying to defend my
Your autonomous system?
My autonomous
Don't
system.
Look at me. Okay.
You know, what is the evidence, and what do I have to be able to go into court and be able to argue? So, you know, we've talked about it very simply as is, so we have to be able to verify that the rules existed.
Yes.
We have to know the requirements. Secondly, did we make sure that the system knew the rules? Were they able to play the game? Were they able to perform the way they're supposed to? So what evidence during the design did we put into place so that we can validate that there were rules, they knew what the rules were? And then you go through the whole the evidence of
precedents.
Precedents.
Right, exactly.
Yep. So in other instances, this is how the court ruled. Here's what happened. Here's what the decision was. So you can pull in
That's a fascinating metaphor.
reusability, and we can start building an evidence case that kind of analogous to developing a court case to be able to argue that this system is validated to be safe. And we can verify that through all the evidence that we've created in arguing our case.
That sounds good. I like that approach, and from both of our experiences, it sounds like it's a very unique and a very fruitful approach to go forward with trying to do this kind of test evaluation, validation, verification of these very complex autonomous systems.
And I think we know we have to do something unique here, because if you look across the autonomy community, this is one of the big challenges, and a lot of people throw their arms up saying this is a hard problem, but you don't see a whole lot of solutions on how to solve it.
Absolutely.
So we're hoping that we will be able to put together a structure and some focus areas that will allow us to at least make progress, if not substantially come close to being able to solve it, so that we can get our systems certified for use.
And at least give people some thoughts that what we're talking about, it'll give them some pause to think about it, and obviously potentially get back to us on some of the ideas and how what they think about this notion of this court case metaphor in order to go forward with autonomous systems.
Yep. And so with that, I think
we're done.
We've talked to you about what our strategy is. We've given you an overview. We've talked about each of our goals. We will come back, answer questions, and we
look at this as somewhat of a living, dynamic document. Certainly, as we get more information, we'll revisit this every once in a while and come back and change what we need to change and update certainly where we are in terms of the science and technology of autonomous systems. And we welcome feedback on this and your comments, certainly.
All right.
Thanks, Chris. Really appreciate it.
Thank you.
Okay.
Great.
Bye-bye.